Now here's my goal today. I'm not going to go through the log normal yet. I'm going to go through Boltzmann again. I mean Maxwell Boltzmann, and I'm going to go through chi-squared a little bit. And I want to mention something in the book. There's at least one wrong answer in the solutions manual, at least, that I've come across. I was doing these things. So I'll try to showcase that. Anyway, we'll do conditional probability. I've got slides about this. I don't know if did I put the slides on conditional probability in chapter 3 up? I will if I didn't. I'll go through. Because they're done really well, and the thing is, it takes the whole chapter, and it kind of condenses it down to what you need to know and why you need to know it, and then we'll apply it to problems. And my own opinion is this. With all the theory that we get, and they can have long discussions about this stuff, until you see it applied to problems, it doesn't sink in. You don't have a good working knowledge. So this is section 2.6. And yeah, let's start with on page 84 in the old text, the Cooper and McGillen, exercise 2-6.3. We're going to start there. I want to do some of these because the exercises don't give you the solutions. They give you answers, and the answers are jumbled. You with me, class? Now, just work with me. I know this is the last day we have Monday off, but please, even if you had how many had an exam today? Oh boy, almost half the class. Work with me in spite of being bleh. So this is an exercise, and this is 2-6.3. Let's see if we can get it. Go ahead.
In a certain gas at 400 Kelvin.
So this is a Maxwell distribution. All right, and temperature was what?
400 Kelvin.
400 Kelvin or centigrade?
Kelvin.
Okay, it's nice he gave it in Kelvin. Some of the problems are in centigrade. Just to mention it, if you have a centigrade temperature, Kelvin temperature, this is degrees Kelvin, is equal to 273.15 plus the temperature in centigrade. And we can do the Fahrenheit one too. The only reason I know that is because yesterday I was doing problems. I don't memorize that. I mean, if you work with it, it stays with you. I knew it was about 270 degrees you add to it. But Kelvin has the same increment in degrees, the same amount of same amount of change as centigrade. It's just the zero shifted. And they give you what? An average velocity is at 600?
Yes, it says that it's found that the number of molecules having velocities in the vicinity of 1 times 10 to the third.
Oh, whoa, wait. They don't give this? Okay. Sorry. So now they say the number of molecules having the velocity of what?
The number of molecules having velocities in the vicinity of 1 times 10 to the third meters per second.
All right, 1,000 meters per second.
And that's twice as great as the number of molecules having velocities
4,000.
that are 4,000 meters
All right,
per
now
second.
hear me on this. Let's first I'm going to put the density function up here. So for a Maxwell-Boltzmann distribution, it's the magnitude of Vx squared, Vy squared, Vz squared, square root of that. That's equal to the square root of 2 over pi. You don't have to memorize this. And it's V squared over sigma cubed, exp, to the minus V squared over 2 sigma squared. You'll notice that the mean value is going to be 0. Y'all hear me on this? I mean, for this one, if you take a look at this, it's because of the symmetry, this is an even function. When you multiply it by V, you get an odd function. You integrate about 0, it's 0. And you'll notice there's no mean value here. For this particular problem, if that's the distribution, he's saying f of v of 1,000 is 2 times f of v of 4,000. That's what he's saying in words. All right? Now, if you look at this distribution function, just to get yourself a mental picture, if this is v and this is f of v, it looks something like this. At 0, it's 0. It's going to hit this, and it's going to come down like this. There's going to be a most probable value, and I'll call it VP here. Then there's going to be a mean value, V mean, and from there we can get the standard deviation. We can do all this stuff. But the first thing we're going to do, y'all with me on what I'm doing? How many have a good feeling, without telling me how to do it, how to do this part right here? All right, what is he really saying? We got f of v, right? So we know f of 1,000, we can put v as 1,000, is 2 times f of v of 4,000, right? You all see this here. That's what he's saying. You with me? It has nothing to do with the probability. It's the probability density function he's talking about there. So the only thing I'm going to do, and just hear me now, I'm going to take this and replace V with 1,000 and equate it to 2 times this with that with V of 4,000. Now you're going to notice something that cancels before I do this. You see how the square root of 2 pi will cancel. Do you all see that? On both sides because we're equating them, right? Matter of fact, let me just do this. So I'll do this way. So f of V of 1,000, which will be equal to the square root of 2 over pi. You don't need to do this. Then it's going to have, I'm just going to leave it as V squared, because I know V here is going to be 1,000, over sigma cubed exp to the minus V squared over 2 sigma squared. That is equal to twice times square root of 2 over pi. Then it's going to be, and this is going to be, V here will be 4,000 over sigma cubed exp, going to have to go through the board's divider, to the minus, and this is going to be V here is 4,000 squared, or plus 4,000, over 2 sigma squared. Now, I wrote that out just so you see what I'm thinking and why I'm doing it. Y'all with me? Everybody? Keep in mind, I'm trying to make this as easy as possible on myself. You see the square root of 2 over pi cancels on both sides? Everybody? Because it's equating. All right, so I'm going to get rid of that. Next, do you all see this? Now, the V won't cancel. This should be, that's sigma cubed, that cancels, right? And that's the Gaussian sigma, so that cancels. Now, at that point right here, I can go ahead and I can put in the values. Remember, that V is going to be 1,000, that V is 4,000. You all with me? So I'm going to do this. I'll just put in 4,000 or 1,000 here squared, and I'll put in the 4,000 right here. So it's 2, and this is 4,000 squared. Try to make this easy on myself. I'll change that in a second. Y'all with me, class? Wait a second. That should be gone. There. You all with me? Take a good look. You follow me? I'm just modifying it to make it easy on myself. Now I'm going to take the 2 times 4,000 squared. What I'm really going to do is if I square this out, I get 10 to the 6th. You all with me? Square this out, I'm going to get 16 times 10 to the 6th. You all see that? So I can get rid of the 10 to the 6th on both sides, right? So here, get rid of that. And now this is going to be 16 times 2, or 32 on this side. I hope you see me. See this, right? Now I've got to put the right value for V in there, 1,000. Agreed? So I'm going to take, actually what I'm going to do is I'm going to put it in first. exp, I've learned my lesson on this one. To the minus, and this is going to be 1,000 squared over 2 sigma squared is equal to 32 exp to the minus 4,000 squared over 2 sigma squared. Y'all with me? Just modifying it. This is the most probable. This is how we get sigma. This is sigma. With me? Now, how do you solve these things? There's several ways. You can use a root solver if you want, right? For sigma, correct, class? But how else would you solve for sigma? Anybody? How about it? How would you for money? How would you do it? Anybody?
Take natural.
That's how I do it. I'll take natural log of both sides. If I take natural log of both sides, I'm going to get minus 1,000 squared over 2 sigma squared on this side is equal to natural log of 32, and then it's going to be minus 4,000 squared over 2 sigma squared. Do y'all agree with this, class? Just take a look. Y'all follow me. Just take it. If you take the log, natural log of an exponential e to something, you just get the something. I don't want to go too fast, but can you all follow what I'm thinking? All right. Now, at this point, this is up to you. I'm going to multiply everything by 2 sigma squared. And I get, I'm doing it this way just because I think it's easier to break sigma out that way. I want sigma. Do y'all follow me, class? Now, at that point, I'll take the minus 4,000 on this side, minus 1,000. So now I get 4,000 squared minus 1,000 squared. And I have to divide it by 2 times the Yeah, 2 times the natural log of 32, right? And that's sigma squared. So if I take the square root of that, I should get sigma. Do you all agree with that? Follow me? And I'm just solving for sigma, which is what? It's the Gaussian standard deviation, right? Not the Gauss. It's not the actual variance that goes, the variance of that distribution. This is the Gaussian variance. Real important you kind of bang that into your head, because this came from Gaussian. We assume Gaussian in Vx, Vy, and Vz. This is going to be the Gaussian associated with the Vx, Vy, and Vz components. So what is this value? Just tell me.
1,470.
Sigma or sigma squared?
Sigma.
Is it that big? Okay. 1,000 what?
471.
1,471. And that would be meters per second, by the way, the units of that. Now, what did they ask for, by the way?
The first one was just asking for the mean velocity.
The mean? All right, that's not the mean. This is sigma. To get the mean for this, and this is the mean velocity for the Maxwell-Boltzmann. So this is V average. That's the square root of 8 over pi times sigma. And you can take a look in the book. You all see that in your textbook? You don't have, I mean, some of this is a little unfamiliar. If you had a test especially, you probably didn't spend a lot of time in this. But you all follow me? Take a look in the book. Circle this. This is the mean, and this is the Maxwell one. Okay, so what is that going to be? Let's see if we get it right. Square root of 8 over pi, and sigma is 1471. 1471, so what's the mean value? I don't know.
I think that's 2347.
Is that what he has, by the way, in the answers? Does he have that down there? It's at the bottom. One of them.
Yes, 2347.
And some of this stuff, he's going to have a little different answer because he's rounding. All right. Everybody with me? Now, what's the next part of that?
The next part is the mass of the molecules.
Okay, first, how many understand what I did there and why I did it? The key is right here, right? Using that equation to get the equalities, right? And I could easily on a quiz say, if the number of molecules at one or moving at 1,000 meters per second was 8 times that at like 4,000, 5,000 meters per second, then there would be an 8 there. Y'all follow me? You would just adapt as needed. Now, what does he want again?
The mass of the molecules.
Okay, this is a little different. So, and you'll get a lot of this in your higher level courses, especially if you're focusing on like device fabrication and plasma physics, reactive ion etching, or anything dealing with gas dynamics and transistor fabrication. You all know that there's a lot of ways to do etching. One of them is reactive ion etching. The other is plasma etching. The other thing is just taking a delineated pattern on a silicon wafer and dumping it in acid like hydrochloric acid. There's all sorts of ways to do etches on silicon and other things. But gas etching, that's what I did my master's work on, was reactive ion etching and plasma etching. And it's just turning a gas into an acid, basically, and then directing the ions in certain directions. So when we take a look at this, first, if you think about, in general, anything moving at a non-relativistic velocity, you know that 1/2 mass times v squared, that would be the energy, it would be the potential energy, right? It's the energy something has traveling at a given velocity. It's non-relativistic, right? If you talk about the velocity, or if you think about this for one molecule, then if you take a look at the expected energy, and I don't even know what he uses for the energy symbol in there, but the expected value of the energy, that would be the expected value of 1/2 m, and it would be v squared, which is really 1/2 m, and v squared here is going to be equal to, did we get that? I didn't put it down here. The RMS, or the v squared for the Maxwell-Boltzmann, and maybe I should just say this is only for Maxwell-Boltzmann, is equal to what? That's sigma, or it's really 3 times sigma squared. Do y'all remember me talking about this? 3 sigma squared, that sigma again is the Gaussian sigma, the Gaussian standard deviation. If it was a Rayleigh distribution, 2 degrees of freedom, it would be 2 sigma squared. Do y'all remember basically that for Rayleigh? If you don't, just kind of go with me on this one. So if I look at that, I can say that this times 3 sigma squared, now that's the energy of one molecule of a mass m moving at a velocity v. With me? It's going to be the energy, the expected energy. Now, I don't know if you had this or not in physics or chemistry. This is from statistics. It's really gas physics and statistical physics. This is equal to 3/2 kT. So this is equal to 3/2 kT. And here, temperature is in degrees Kelvin. Kelvin. And K is the Boltzmann constant, which is 1.38 times 10 to the 23rd. All right, and that's joules, degrees Kelvin per second. But don't worry about this. It's actually a little more. It's 1.381, bunch of stuff. You remember these constants? There was Avogadro's number. This is right here. That's Boltzmann's constant. There's Planck's constant. Do you all remember speed of light, c? There's about 5 or 6 constants that you use all the time that are based on statistical mechanics of the different phenomena. With me, class? All right, now for this, you can see the 3/2 cancel, right? And now you can see that sigma squared is equal to kT over, actually, we want m, pardon me. We want m, that's what he's after, I think, in one of these things. It's going to be kT over sigma squared. So if you can do this with me, it's 1.38 times 10 to the 23rd. Temperature is, what was it again?
400 Kelvin.
So it's times 400. And it's, what was sigma squared for us? Somewhere. Where did I get it? So it's 1471, and I got to square it. Right? 1471 squared. Can you tell me what that is? Because this is minus 23. My bad.
Yeah,
minus 23. I'm so sorry.
Otherwise, it should be
I'm so sorry. What is that? It's small. It's like 10 to the minus 27.
0.255 to 10 of negative 26.
So 2.55 roughly times 10 to the minus 23rd. Wait, is that the right answer?
He got to the minus 27.
I mean, look, 27th, pardon me.
Yeah.
Is it 2.55?
It got
2.5.
5.3, so.
Pardon me? 5.3? I'm going to bet it's something with rounding.
Round.
Because the real Boltzmann constant's got a few more numbers after the 8.
Yeah, the Boltzmann constant is 1.38 times 10 to the negative 23.
Yeah, but that's rounded. When I use the exact value in MathCAD, it's a little different. It gets his number, I believe.
Okay.
I believe. Okay, so that's right. What's the next part? This is a good one.
That's all for this question.
Now, some of you are wondering, well, do I have to memorize K and T? I'll give you K. Don't worry about that. But the KT, you have to, normally the energy in a molecule moving at a velocity v is equated to 3/2 kT. That's what I did over here. Energy is 1/2 mv squared. V squared is found from that equation, which is 3 sigma squared for the Maxwell. Follow me? So 1/2 mv squared should be familiar to you as the energy. You replace the v squared with 3 sigma squared. That's equal to, in the energy in terms of temperature in a gas. And this is not a gas with any kind of skewing. You don't have electric fields and stuff and magnetic fields affecting it. It's just 3/2 kT per molecule. Has anybody heard this in chemistry or physics? What class do you remember? Yeah, and this is, by the way, gas chemistry. This is not something, solid state chemistry is a little different. I had crystal chemistry in graduate school, and man, that made chemistry clear. Undergraduates, a lot of memorization, a lot of stuff you don't know why it's happening. There was a guy named Linus Pauling. You know that name by any chance? Anybody knows? What's he famous for? He's a chemist. 2 Nobel Prizes, would have had 3 because he did untangle the DNA helical stuff, but he didn't get credit for it. He sent it to 2 guys who got it. Brilliant guy. He's I think he was at Caltech or at at Berkeley or Stanford, one of these. But he's a brilliant guy. So this guy was famous for vitamin C, because he's the guy that read Norman Cousins' book. If you ever want to see something that's revealing, look at Anatomy of an Illness by Norman Cousins, and how he's almost dead, should have been dead, and he found that he used IV vitamin C at 25 grams per day, and he completely healed a disease that should have killed him. And in all other cases, it killed him, but the press never gives him any credit. Anyway,
You said the book's called Anatomy of an Illness?
Anatomy of an Illness. It's by Norman Cousins. He's a famous guy at the Saturday Evening Post from years gone by. This is before you guys were born. But it's interesting to know all this stuff. Trust me, it made a real impact in my life when I had problems, health problems. Anyway, Norman Cousins was the guy that wrote The Nature of the Chemical Bond. This book took chemistry and said everything that goes on there has to do with minimum energy principles and plus or minus attractions, or plus plus or negative repulsions. So how come you get these weird shapes and all that? And he did it from an electrostatics perspective. It's brilliant. And I had this in graduate school, crystal chemistry, and all of a sudden, now it makes perfect sense. It didn't when I took chemistry. It's like, why? But do you all feel that way? I mean, how many have had basic chemistry? Anybody had like any kind of advanced stuff with like gas thermodynamics? I mean, did you have statistical physics part of chemistry? What do they call it? Physical chem? Yes, but it's taught in chemistry, as I recall. The one I had is, and I mean, that stuff's phenomenal. Also, I want to tell you one other thing, and I encourage you to do this. If you ever have a class as an undergrad that's just like an overview of a topic, and you come out scratching your head like, I don't know how they got what they got, don't worry about it. If you're really interested, wait until grad school. They really start opening up all the things, the proofs, how they derive what they got. Back to this problem after that long-winded discussion. So that's it?
That's all for this problem.
Okay.
And then we go into chi-square distribution after this.
Yeah, all right. Chi-squared's kind of interesting. And I'm going to tell you one thing. This book is very sparse about it, but it is a very important distribution nonetheless for all sorts of things where they're sampling something and they're trying to conclude something of predicting what else is going to happen. You're going to have to just go with me on this and read them. Has anybody read the text on chi-squared? Have you? He talked about statistical sampling and things, right? And there's something to that effect. And it's used all the time, but until you see the real usefulness of it, you're wondering, why are we talking about it? They normalize this. I'm not going to normalize it for some of the problems, but I'm going to show you how to do them. So in the book that I'm using, the old book, Cooper and McKillen, here's what he does. There's problems in the back on this one too. Why don't we, before I get into chi-squared, why don't we take a look at the problems in the back of the book? I think it's 2-6.5, and do the ones that he's given us regarding Maxwell-Boltzmann, so we can just apply it to some more problems where you see it. And I'll ask you how to do it. Can you tell me which one it is? Is it 2-65 or 2-64? This is problems in the back.
We've got a 2-65, talking about average speed of a nitrogen molecule.
Yeah, that's it. Now this, anytime you see molecule, gas, anything like that, Maxwell, right? Anything you see marbles rolling on a flat surface or velocities in 2D, Rayleigh, all right? One-dimensional stuff like power is I squared R. That's just that's going to be a skewed normal. Right? Go ahead.
Okay, so the average speed of a nitrogen molecule in air at 20 degrees Celsius.
All right, so temperature is 20 degrees Celsius, and that means the Kelvin temperature, this is degrees Kelvin, is going to be 273.15 plus 20, or 293.15. All right, so go ahead.
And then it says it's about 600 meters per second.
All right, go ahead.
And then the first part wants you to find the variance of molecule speed.
So they're looking for sigma squared, right? Now, I'm going to say this. I'm going to get the sigma squared of the Vx, Vy, and Vz. Y'all with me on this? So I'm getting I'll put this down. This is the one I'm going to get is Gaussian. In the text, you'll notice that sigma squared for the Maxwell-Boltzmann distribution, in other words, the actual magnitude of these things, This is actually equal to 0.453 times that sigma squared, where that's Gaussian. Anytime sigma does not have a subscript, assume Gaussian. You with me? Do y'all remember that 0.045 or 0.453? How many do? Anybody? It's something I would give you that. You're gonna have too many constants rolling around in your head to memorize if I don't give you some of them. All right, now, from that, how do we get this? Well, remember, I didn't prove this. You can actually do the integration of that function. Remember, f of v I put down was square root of 2 over pi times v squared over sigma cubed exp to the minus v squared over 2 sigma squared, right? If you take that and multiply that by v, where you get a v cubed now, and do the integration for the mean value, you actually come out, it goes from 0, by the way, not from minus infinity, it goes from 0 to infinity. Then you will get what I'm about to show you. So v bar, and this is the average value, not the square root of the RMS value, is equal to square root of 8 over pi times sigma. Now that's Gaussian sigma, just remember that. And he has this in the text. Can you tell me where it is in the text? Just look back in the section on Maxwell. He has this equation, I promise you. At page 83, star that equation or do something to denote it in your notes. This is kind of an important one. All right, now, from that, you can see that sigma itself is going to be equal to the square root of pi over 8, right? And it's times the average velocity. So in our case, it's square root of pi over 8 times v bar, and v bar was 600. And I don't know what that is, but you can give me that in a second. But to get this value, and he wants the sigma for the Maxwell-Boltzmann, right, for the action. This is going to be 0.453, and then I got to take that value and square it. So it's really going to be times pi over 8, and it's times 600 squared. So what's that value? Y'all with me? You know what I'm doing, right? I'm just using a formula to get the value. This is the important one right there. So tell me what that is. 14, help me. 14 what? 141,372? Is that right? Right? I don't know. It looks right. And that would be, that's not, wait a second. No, that's v squared. I mean sigma squared. Hold it. Just take 600 times square root of 8 over pi.
Oh, that's 375.
Thank you. All right, so that's 375 meters per second. Now, over here, what's this? I should have just left this sigma squared. Take that value, 375 squared times 0.453. What is it?
64,041.
That's big. 64,000 what?
41.
041, sorry. 041, and that would be meters per second squared. And y'all with me? By the way, MathCAD, has anybody tried MathCAD yet? If you get a chance, do it. Download it and try it. And here's why. It does the units for you. It'll get all the units, has all the constants. And for me personally, it's very useful if I'm doing weird stuff where I got chemical reactions, thermodynamic stuff thrown together. Is that right, by the way?
He doesn't have the answers unless they're in the back of the book.
What answer for you? It's on OneNote, right? I put the solutions to this book.
Yeah, on the laptop out.
Don't worry about it. Anybody? I think it's right. I think it's right. He's checking. That's part. This is part B.
Oh, that's part A.
Okay, so this is part A right here. I think it's the right answer. Somebody's going to check. You got 6.5, and it would be part A. Whatever. Okay. What's the next part? Remember, you have to get the sigma from the Gaussian to get this. I need to get that value to get this value right here. Now, in fairness, I'm not going to. If I repeat that equation for the Maxwell distribution, the square root of 2 over pi, v squared times v squared over sigma cubed exp to the minus v squared over 2 sigma squared. If I take that and multiply it by v minus the average value, and then do the integration from 0 to infinity, I'll get this. but I'm not going to do that. It's a pain in the butt integration if you do it by hand. Okay? What's part B?
Part B is find the mean value of the speed.
Just mean.
Just the mean value.
Isn't that the mean value?
Yes, should be.
All right, but he meant, I think, the R.
Oh, no, I'm sorry. I was looking at 2 Tech 6.4. It's the most probable molecule speed.
Okay, sorry. Most probable molecule speed. Now, I'm going to I have to put the distribution back up. So f of v is equal to square root of 2 over pi times v squared over sigma cubed exp to the minus v squared over 2 sigma squared. I know I harp on this a lot. That sigma is Gaussian. Anytime that you don't have a subscript, it's Gaussian. With me? It has to do with the Vx, Vy, and Vz distributions. And I can't state that clearly enough. With me, class? Now, keep going on this one. That would look, and this is only for v greater than 0, less than infinity, or equal to infinity. Technically speaking, all right, there is no negative values. You could say for negative values, it'd be 0. So here, if you look at v, it does something like this, and this is not drawn to scale. And this is the most probable value, the peak value. And how do we get that, guys? We've done this several times last time. Anybody? Derivative and set it equal to 0, right? You okay with that? I probably bore you, but I'm trying to underscore what's critical, what I think is very important you know. Because a lot of people just don't know what he's talking about. Most probable, it's the average value. That's your gut reaction a lot of times. It's not. Most probable has to do with the density function and taking a derivative of it, setting equal to 0. That's the peak in the probability density function. And there will only be one for these. So if I take a derivative of this, here's how I do these things. I'm setting it equal to 0, right? You see how all this stuff really is going to go away? So just ignore it. Take a derivative of the remainder and set it equal to 0. Make sense? So if I take a derivative with respect to v of, and that's going to be v squared exp to the minus v squared over 2 sigma squared, that's going to be what? Well, the derivative, and I'm going to set it equal to 0. Derivative of the first is 2v times this exponential plus the first, which is v squared, times the derivative of the second. Now, a derivative of that exponential is the derivative of the inside part, which is going to be minus 2v over 2 sigma squared, or just minus v, because the 2 will cancel. And it's going to be over sigma squared here, right? And then it's going to be times the exponential of minus v squared over 2 sigma squared. Just take a look at that. I hope you all agree with that. I just took a derivative. Set it equals, you with me, class? Now, well, this is how I do these things, and it's nice to do these on a whiteboard or on a pad where you can just erase stuff you don't want. You all see here that the exponential on both sides goes away. So first thing I do is that. Next thing I do, that's a minus. This is really v cubed over x squared, right? Or over sigma squared. You all agree with that? Now, equate them. So I can divide by v too. If I divide by v and take one to the other side, I have 2 equal to v squared over sigma squared. Convince yourself of that. You all see it? And now I'm solving for v, right? You all see what it is? V is just equal to the square root of 2 times sigma. And that is the most probable velocity. And so let's see if we get the right answer. So that means v, and I'm just going to call it most probable, is equal to square root of 2 times sigma. And that's the Gaussian sigma, which is there, right? 375. And what do you get for that? It's all right. You don't have to do it.
530.
530?
Yes.
What? 530? I mean, that's Right. Now, what's the next part? That's part B. Part C?
The last part is the RMS molecule speed.
Now, that's VRMS, right?
Yes.
Now, I'm going to tell you something. I believe this answer is wrong. The actual, if you think about this, I think I put this up here. When I looked at V squared bar for the Maxwell one, I put down 3 sigma squared. Do y'all remember that? Or 3 times sigma squared. Remember for the Rayleigh, it was 2 sigma squared? Y'all remember me talking about that? You might not remember exactly. So do that and tell me what this value is first. Now remember, that is V, this is going to be the second moment, all right, of this distribution. Y'all with me? So what is that? What did you get for that? 421,875 meters per second squared, all right? That's 3 sigma squared. Take the square root of that, what do you get? 375 times what?
649.5.
All right, I think he has the wrong answer. 6 what? 40?
49.5.
All right, do you all see that? That's meters per second. Now what he did is this. He used this sigma and he multiplied it by 3 and took the square root. That's wrong. You have to use the actual sigma associated. I think he did. Does he have, he didn't have this answer, does he? He's got like 530 or something like that?
No, just have it on the laptop.
Or 2 something, I forgot. What does he have?
It says 253.
Yeah, that's wrong. 253 ain't the right answer. That's when you take 3 times the square root of that, if you do it. He's wrong. It has to be VRMS squared, all right, the square root. That's this 3 sigma squared, wherever I put it down, that is the RMS velocity of a Maxwell distributed gas. With me, class, on that? Do you remember when we even used that for the energy calculation? 1/2 mv squared, right? Now that's a wrong answer in the solutions manual. Make note of it. They make mistakes too. I checked on this one. Okay? Is there another part?
That was the last part.
All right, let me ask you this. You don't have to do this, but I'm asking. If all of a sudden I said you get to use your calculators and stuff, and I wanted the probability, hear me now, the probability that the velocity would be less than the most probable value, what would you do? I mean, if it was less than the mean value, it's a no-brainer. It's 1/2, because the mean value, 50% above, 50% below, right? But the most probable value, you would have to do an integration, either one of 2 ways. Either integrate that density function from here to here, and that's a numerical integration, right? Or take 1 minus the integration from here to here of that density function. But that's how you would need to get it because there's not a closed form thing like what it is with the Rayleigh. And we don't have tables available for that one in the back of this book or the other book, as far as I know. I don't think. You can do it numerically with your calculators, and he makes mention of that. I am not going to do that to you. But when you get into higher level courses, especially whenever you get into anything with a lot of statistical stuff like communication systems, all this other stuff, they'll ask you to do things like this where you need to be able to do numerical integrals on your calculator or have available on your laptop some way of doing it. Is that it for that problem?
That's it for
Is
that
there
problem.
another problem with Maxwell Boltzmann or air or anything like that?
He's got the marbles rolling on a
No,
flat
that's
surface.
2D. That's 2D. That's Rayleigh. How about 6.6? I think that's chi-squared, right?
I think so, yeah, because 5 independent observations of a Gaussian random voltage.
That's chi-squared. Now we're going to go do chi-squared, okay? And do you mind the way I'm doing this right now? I've got plenty of theory I can teach, but I got PowerPoints, but applications, I think, is where you see it. I had a couple of teachers that I really appreciated. What they would do, they'll give you reading assignments, and they will, present the theory kind of quick, but then they would spend time applying it to problems, especially complicated problems that confuse you. And that's where you really learn. And especially if you take a swing at the problems, try them, and realize, I don't know how to get this part, and then have that question answered when you come to the lecture. Didn't physics used to have a resuscitation where they'd have a long period where they just go over problems and how to, that was smart, I think. So now this is chi-squared distribution. So for the chi-squared distribution, it's a density function, but now it talks about this thing's going to have to do with the number of degrees of freedom of the event. And they're assuming this. The way he shows it in the book, he has this in an odd way. He says x squared average. Now this is a random, or he's saying x squared. This is a random variable. Is based on y1 squared plus y2 squared plus dot, 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 plus y to the n squared. And each one of these, the fy of y, is going to be a normalized Gaussian distribution, which means the mean value of all the y's is going to be 0, and the standard deviation, or the variance, is 1. So he's assuming for these fy's of here that these are going to be 1 over square root of 2 pi exp to the minus y squared over 2 sigma squared. And he's saying that what I'm going to do is create a new variable. Remember, this is f of y, not f of y squared. That is made up of, it's just going to be the sum of the squares of all these normalized random variables, Gaussian random variables. Try to just hear me before you think too deeply about this. This is relative statistics where we're sampling things and squaring them so we don't have negative values. And we're going to get statistical information about sampling something either n times, that would be n degrees of freedom, or having something where we're going to sample an event at n different locations. All these things have a Gaussian distribution and 0 mean with a standard deviation of 1. Some of this is going to seem a little odd, but you just work with me, okay? So the chi-squared distribution that comes from this, the way he has it in the book, he does it with x squared here, I think. And I got to be careful about this because chi-squared usually just has a single argument, doesn't have a squared argument. And the way he does it, I'm going to put down, this is not something, you might not see this form on Wikipedia. They may use x squared as a single variable, all right, like y or something. But so I looked this up. But the way he's going to do is leave it in terms of x squared, and it will be to the n over 2. I forgot. Is it n minus 1 over 2 or n over 2 minus 1?
It's n over 2 minus 1.
Yeah. It's that over, and here you're going to have 2 to the n over 2. Then you're going to have a gamma function. This is called a gamma function. You'll use this later a lot. And that's going to be of n over 2. These are single values. If n over 2 is going to be integer, this has a simple form, but it's going to be n over 2. And then it's just the standard exponential. Now, a couple things to note about this. One is, in order to use this for anything, what he's going to show you is this. I'll just tell you this. He's going to show you that the mean value of x squared is just n, and n is the number of degrees of freedom. There's a very formal definition about this, but I'll try to make it as clear as I can. So if you have something that only varies in one dimension, say you're shooting a marble down a track, and the velocity distribution on that marble is Gaussian. It can have both negative and positive values with a 0 mean, a standard deviation of 1. That would be a chi-squared distribution because it is based on a Gaussian, the Gaussian profiles of where n is 1. It would have 1 degree of freedom. If you're rolling marbles on a table, something like this, and the Vx and Vy distributions had a 0 mean, they're Gaussian, with a standard deviation of 1, and you're getting the actual magnitude of velocity, it'd be square root of Vx plus Vx squared plus Vy squared. That would be a problem that has 2 degrees of freedom. And it would actually be the Rayleigh distribution if you normalize the normalize the standard deviation. I'll talk more about this after I get through this. If you have a Maxwell distribution and you normalize the density functions for fx, fy, and fz so that they have a sigma value of 1 and a mean of 0, which the mean is always 0 for that, then it would be the chi-squared with n equals 3. It would have 3 degrees of freedom. When you talk about higher ordered or more degrees of freedom, you're really talking about something where you're sampling events that have a standard deviation of 1 and a mean of 0 that are basically Gaussian random variables. Do y'all follow me in this class? Just try to bear with me on this. Some of this is a little obscure until you see it applied. So if that's the case, if they're all normalized, then the mean value of x squared, which is the variable x squared here, this could be called something like g or q. They do that most of the time. Then the mean value of this would just be n, where that would be the number of degrees of freedom. Then in the book, and this, I don't like this, he's going to show this squared. I think you can see this. This is 2n. Now, he has this in the book. This is kind of odd because he doesn't tell you how to normalize a distribution. Do you all hear me on this? So when you have a velocity distribution or a Gaussian distribution, let me just tell you what I mean by this. If you have f of x, and it's not normalized, then it's equal to 1 over the square root of 2 pi times sigma exp to the minus, and here it's going to be x squared over 2 sigma squared. Now, when they say normalization, one of the first things, the knee-jerk, is just divide that. If the standard deviation was 9, divide it by 9. That would be wrong. If that integrates, you have to have a value of 1 over from minus infinity to infinity. It won't be 1 if you divide that by 9. Do you all follow me? So when they talk about normalization, what they're really doing is this. What they're talking about is now we're going to create a new function, call it f prime of x, and we're going to say that's f of x, and then it's going to have, you're going to divide the sigma by itself, you might say. This is not going to come out the way I want, but you're really going to have the actual sigma divided by itself. So it will get rid of this, and it's going to get rid of this. So basically, you're going to have this when you normalize. But you have to remember, you've taken sigma and divided it by itself. Just bear with me on this. Now, the mean of this will still be 0. And the standard deviation of this will be 1. So if you want the actual standard deviation, you multiply that by the normalization factor squared. I mean, that's standard deviation. So the variance of this will be equal to 1. Take that and multiply it by sigma squared to get the actual variance. I hope you can appreciate it. I'm not trying to make this too hard, just saying what they're talking about without doing it. Now, most of the time, if you want any statistical information with a chi-square distribution, you have to do the integration of this thing most of the time. Not all, but most. Y'all with me on that? This is a pain. It's a numerical integration. That gamma function right there has easy values if n over 2 is an integer. Like if n is 2, 4, 6, 8, it's easy. If n is 1/2, it's not easy. If n is 3/2, it's not easy. Then it's an integral. And I'm not going to put down what the mathematical function for that is, but it's all over the place. And they have all sorts of expressions, from integral expressions to infinite series expressions. You must have had this. You've done this in physics, haven't you, the gamma function? There's several different expressions for this that I'm not going to worry about right now. Later on I may, but your calculators do it. Look up gamma function. Gamma, capital G sometimes. It's in your calculator. Almost guaranteed. Almost. So now let's do first the example problem. And can you help me with the example at the end of that section?
Yes, it's exercise 2-6.4.
2-6.4. Go ahead.
and you have 12 independent samples.
All right, so that means we have 12 degrees of freedom. That's the only thing I'm saying. Okay, go ahead.
Of a Gaussian voltage are taken, and each sample is found to have zero mean and a variance of 9.
Oh, those rats. So now they're saying a variance squared of 9, not 1, 9. They're such rats. Okay, go ahead.
And
Sorry.
then a new random variable is constructed by summing the squares of these samples.
So I'm going to just say x, and this is going to be x squared here. I'm calling it x squared the way the book does. You can call it g if you want. Is equal to, and there's 12 of them, so it's the sum from I equals 1 to 12 of, and now it's going to be y of I squared. Go ahead. Y'all follow me on this? I'm just writing down mathematically what he's talking about. It's got 12 variables. This would be the actual variable. I could write it out 12 times, y1, y2 plus. I'm doing it this way. Okay, go ahead.
And then I want you to find the mean.
All right, now, hear me on this one. What he really wants, the expected value of x squared, right? He wants the mean of, that would be the expected value of x squared, correct? Now, if you look at this, that's the expected value of y1 squared plus the expected value of y2 squared plus plus the expected value of of y12 squared. And here's where you got to realize, remember the distribution for y here is assumed to be Gaussian. Go with me? So if you look at this, if you looked at the expected value of any of these y squared, right? That's really equal to the sigma squared of y, that would be the Gaussian, plus the mean value of y squared, right? You all agree with that? What's the mean value of y? Said in the problem?
0.
0 for the Gaussian distributions, right? 0. So it gets rid of that. It's just this. Now, if you look at these, each one of these has an expected value of sigma squared. Sigma squared is 9, isn't it?
Yes.
And there are 12 of them, aren't there, class? So if we look at this, this is really going to be 12 times 9, or 108. And I think that's one of the answers.
Yes.
All right, you all with me? The next part is the screwy part. Okay. Now he asks for this what?
He wants the variance of the new random variable.
Okay. Variance of the new random variable, right? I'll try to do it right here. So in general, what he's talking about is the expected value of the random variable is x squared, right? Minus the mean, minus the mean value of that squared. Do you all agree with that? And really, you can think about the expected value of, if we had a variable, and what did I call it? G. Here, you could say it's this, G minus G bar squared. And that would be the variance of y. Do you all agree with this? Of x, pardon me, x squared, variance of x squared. With me, class? Now, if you think about this, the variance of anything, doesn't matter what it is really going to be what? The expected value of that anything minus what? The average value of that anything squared. Do you remember that? That would be the second moment minus the average value squared, right? Okay. Here's where it gets fun, sort of. So when we did this, we found the average value of y is 108. Take note of that. That's just, or x, that's x squared bar right here. We'd have to take that and square it right here. Do you all with me? Now we need to get this guy. This guy's a little more fun. Not really, but I'll show you what I mean by this. You could integrate this, by the way. I tried to do that, but MathCAD's FlexLM license wasn't working yesterday or today. So I can't, I can do it on MATLAB or on Mathematica, but I didn't choose to do so. But I'll show you the way to do it. I think this is going to work. And I hope I don't make a mathematical multiplication mistake. So if we take a look at the expected value of x squared, right? It's actually, what? It's the expected value of, pardon me, of x squared squared. Do you all agree with that? This could really be written as the expected value of x to the fourth minus g bar squared. And instead of g bar, why don't I just put it down as the value, give me 1 second. So it's 108 squared. I'll just put it as 108 squared so you'll know. All right, how do we get this? Well, what this really is the expected value of, now what is x squared? It's y1 plus y2 plus plus y12, right? Squared. Do you all agree with that? Because that's what x squared is, right? Take a look. You all agree with this, class? So what happens when we square this thing out? Don't we get the expected value of 144, and then it's going to be of y to the fourth. Isn't it, class? I mean, each one of these has the same statistical properties. So if you have 12 variables here, you're multiplying by 12 more variables. That's 144 variables with the same statistical information. Do you agree with that? Now, that's 144 times y to the fourth. Just think about it. y1 times y1, y squared. Y is going to be, I'm sorry, it's, let me say this again. These are squared. My bad. My bad. When you multiply them out, you're going to get y to the fourth. You all follow me? I'm sorry. But you're going to get 144 of them. So if you think about this, this is really going to be 144, and this would be equal to the expected value of my x squared squared. 144 times the expected value of y to the fourth, right? Well, what is the expected value of y to the fourth? Remember, y itself is a Gaussian random variable, right, with zero mean. With me? So if you remember back, that means this is 144 times this business. 1 times 3 times, and it's n minus 1. Since y is 4, we stop at 3, right? And then we get sigma to the fourth. You all with me? That's a pain, isn't it? All right, so this is going to be 144, right, times 3. Sigma squared is 9, so that's times 81, right? Just write it down. Don't do it yet. So if I take that over here, then, if I did this right, and I hope I did, would be equal to, what is that? 144 times 81 times 3, or 3 times 81 times 144 minus 108 squared. What do you get for that? Because that ain't going to do in my head. So the variance is 23,000. Say it again. That's the variance. What would the standard deviation be? Square root of that? 152?
That's what I got too.
I think he has like 19 something. 1900?
Yeah, his answer for the variance is 1944.
See, I believe this is right. Now, I don't think I multiplied anything wrong. You can check me on that. But you all follow me, the reasoning behind it? And I'm going to say one other thing. I'll do the chi-squared integration. I'll look at this. In his book, does he actually, I didn't look at the solutions. I got the solutions here. This is 2.6.1.
2 tag 6.4. It's exercise.
Oh, it's an exercise. I don't think he has the exercise. I'm pretty sure in the book that's wrong. I mean, I think that's a wrong answer. I think that's right. I'm almost positive. I'll double check that. I'll do the formal integration, but I think this is right. Now, I want to do the problem in the back of the book relating to chi-squared. You're going to believe it is. And the reason is I went through and formally did the statistics on this. If I messed up, I tend, if I'm really working fast, to multiply things wrong. But I think that's right, okay? So now let's go to the back of the book and do the problems. These answers I got complete. So related to this, this is, I think 2.6.6 is the first one, right?
Yes.
We can't get the log normal today. All right, so 2.6, go ahead.
You have 5 independent observations of a Gaussian random voltage.
So he says we got 5 random, this is 5 degrees of freedom. Go ahead.
With 0 mean
Velocity is 0, right?
and unit variance
Oh, that's so nice. Go ahead.
are made, and a new random variable x squared is formed from the sum of the squares of these random voltages.
All right, V1 squared plus V2 squared plus plus V5 squared. These are just observations. Go ahead.
And then the first thing is asking to find the mean value of x squared.
Hear it? All right, what he's really saying is he wants the expected value of x squared. I wrote the equation for this. It's just n, all right? But if you have everything normalized, and it is in this one. But I'm going to just show you what he's really talking about. So it's the expected value of V1 squared plus the expected value of V2 squared plus the expected value of V5 squared. These are all these are Gaussian random variables, the V's. All right, so V squared, the expected value of that, is really the second moment. And if the mean's 0 for the Gaussian, it's just sigma squared. You all follow me in that? So this is really going to be 5 times sigma squared. Or 5, and sigma is 1, so it's 5. And I think that's the right answer, if you can confirm that, anyone. Does that, he have that as the answer in the book? I almost guarantee it's right. Somebody just confirm that. Go. What's the second part?
The second part is to find the variance of
All
x
right.
squared.
Now, this part B is the variance. In the book, he has sigma squared of x squared, his new random variable, is just 2n, or it would be 10. Now, you can use that equation, but if you wanted to get the variance, right, technically speaking, you'd say that variance was the expected value of x squared, right, minus the mean value of x squared. I don't like that squared business, but he does that in the book, so I'm showing you it the way he does it. We've got this as 5. We could get this, right? What would that be? Well, what would I have to do? I have to take this. There's 5 of them, multiplied by itself, right? I get 25. Do you all follow me on this? Then I'd have to go through, and I'd say 25 times the actual, and this would be this, sigma to the 4th would be there, right? Well, sigma is 1, so it'd be 25. Does he have 10 down there? He should. No. Okay, with me? Just, you can do the math on this one. I believe it works out. What's the final part? Go ahead.
The last part is, what is the most probable value of x squared?
Do you remember doing this? Well, we found what? For the velocity, when we did the velocity one for the max, for chi-squared, there's 5, sorry. We're going to have to do the stupid derivative on this one, right? So if I write the chi-squared distribution for this, we did this, but I'm just going to tell you this. The f for 5, right? So it's I'll call it just f5 of v. That's equal to, and he likes to put an x squared there. I'm not a fan of that. So he's going to have x, I wish he didn't do that. Yeah, he does have x squared, gosh. And he's going to have this to the n over 2 minus 1 here. And then he's going to have downstairs, he's going to have that gamma function to the n over 2. And then he's going to have, what is it, sigma?
It's 2 raised to the n over 2.
Sorry, just 2 raised to the n over 2, which is weird here. Oh yeah, it's normalized, never mind, sigma's 1. And then it's going to be times exp to the minus, and it's going to be x squared over 2 sigma squared. You all with me on that? He'll have that down there, right?
With the normalized, he doesn't have the sigma squared and the
Oh yeah,
exponent.
sigma's 1, never mind. It's just 2, right? All right, if we want the most probable value of that, n is equal to 5, right? right? So we've got 5 halves minus 2 halves, or 3 halves, right? 3 halves, x to the 3 halves power is going to be, x squared, I mean, to the 3 halves power is x cubed on top, right? Just watch me on this. Now, n here is equal to,
5.
so this is 2 to the 1, or 2.5. This is a constant, just put a 5 in there, but here's my point. Now, if you look at this and you want the most probable value, what do you have to do? You can forget this. All right, just, isn't that a constant right there? This is all a constant, right? So if I want the most probable value, I'm going to take the derivative and set it equal to 0. Do you all with me on this? If I take a derivative of this and set it equal to 0, I'm going to have 0 is equal to 3x, just leave it as x, squared times the exponential of minus x squared over 2 plus, and you forget those constants, plus x cubed times the derivative of that, which is going to be minus 2x over 2, or just minus x, and times the exponential. So when I set it equal to 0, I can get rid of the e to the minus x squareds here, and I can see that really I get 3x squared is equal to x cubed, or I simply see that 3 is equal to x, if you look at this. Are you agree with that?
Would be x to the 4th minus.
Oh, I'm sorry, you're right. It's x to the 4th, my bad. So this is x squared. Let me do it this way. So this is really going to be x. 3 is equal to x squared. Since x can only be positive, it's the square root of 3, right? Do you agree with that, class? Is that the right answer? You all with me on this, class? But that's how you do it. What else does he ask?
That's the last.
That's a fair problem. The one where he talked about the standard deviation, or the variance of y, I think his answer is wrong on that. I'll do the actual integration, but I'm pretty sure it's wrong. Okay? We're out of time. Everybody knows when the test is, so here's what I'm going to do. We didn't get a quiz today. We don't have class Monday, right?
Correct.
All right, so on Wednesday, I'm going to give you a quiz related to sections 2.6, 2.5, and 2.7. All right, so you got, that's the Rayleigh distribution, right? That was 2.5. 2.6 is what we just covered today. I won't give you something with log normal, or we didn't even cover that, or the chi-squared. But Boltzmann, Rayleigh distributions, and just Gaussian. And then for section 2.7, it was the uniform density, exponential density. Did we have another one in there? Oh yeah, the what do they call it? Erlang distribution, right? But those are the distributions in the problems. So do the problems in the sections. I can give you some additional problems out of the book, the original book. We're going to use that thick one. I'll give you some of those things with answers. And then we'll have a quiz on Wednesday, okay? If you want, we can do the quiz first thing. And I'll give you like 15 minutes, okay? And that way I can jump right into the lecture without having you guys just thinking about what are you going to quiz on. Okay, did you all understand today?